So welcome to our last lecture in probability review, the sixth one. And this is a very important one because we're going to be talking about conditioning, and we'll look at how we can find expectation through conditioning. In this lecture, we will cover conditional probability. We'll review Bayes' rule again and show how we can make it really applicable to a lot of problems given what we know about distributions now. And we'll talk about expectation and how we can find it using conditioning. So we can now express Bayes' rule using these probability distributions that we've talked about in the last few lectures. And the way to think about it is that if we have now a set of variables, and this X now is actually a matrix, and we can think about it as a matrix where the columns represent each one of the variables in our random vector that describes some particular area of interest. For example, if we're thinking about a patient in a hospital, the X values, each separate X and each separate column can represent things like blood pressure, temperature, body mass index, the results from a test, for instance, the amount of low density lipoprotein in the blood. All those kind of things can be represented by the columns in X. And the rows would represent individual patients, then the observations that we have. So we now have basically a large data set that we can think about. And the theta, this bold theta, is actually representing all the model parameters that we might have. And we've seen examples of those before. They can be, for instance, things like the mu or mean vector in a multivariate Gaussian. They could be the matrix, the covariance matrix in a multivariate Gaussian, things like that. They're all combined within that theta. So now looking at Bayes' theorem, we see that we can look at finding, for instance, the probability of those parameter values in those models as what's called the posterior distribution given the data. So this is after we observe the data. And on the right-hand side, we see there's a prior for those parameters, which is what we think that the uncertainty is around the parameters before we see data. The likelihood function then gives us the distribution for observing the data given the parameter values, and the denominator is what we call the evidence. That's the probability of seeing the data. So notice that we can find the denominator in Bayes' theorem using the sum rule, and actually we will now call this conditioning because it's really conditioning on the values for that we've either seen or we're assuming that we know. So for example, in the case of finding the data set X, we could consider that by first finding or assuming that we know the values for Y. And then basically what we do is we use the sum rule. We're saying, fine, let's look over all possible values for Y for the likelihood of seeing those values of X. And then we multiply that by the probability of seeing those values for Y. And this is, of course, the discrete case. In the continuous case, we replace the summation with an integral, and we replace the probability mass function with a probability density function. Okay, so we can use these kind of ideas then to find expectations. And as I said, this is going to be something we're going to do over and over again in this course. It's a convenient way for us to take a problem that's complex and solve it through a series of conditioning operations. And the idea is basically if we want to find the conditional values for X, we don't know them right away, but we know something about X through Y. Then first we find the expectation of X given Y, and then we find the expectation for that result, in particular by looking over all possible values for Y. Okay, so in the discrete case, it looks like this. The expectation of X given Y is within this summation, and then that's times the probability of seeing all values of Y. And that returns for us then the expectation of X. The continuous case, again, same thing. The only difference is that instead of a summation, we have an integral, and instead of the probability mass function, we have a probability density function for y. Let's look at a very simple little example of how we use conditioning. Suppose that n is the number of accidents per week on I-95. And let's let xi, where I is one of those accidents, be the number of injuries in the accident. Then the question is, what is the expected number of injuries per week? And we'll call the number of injuries per week I, and we're looking for the expected number, so we want the expected value of I. Well, we can solve for this, and the way that we're going to solve for it is by conditioning on n, on the number of accidents per week. So to do that, we then say the expectation of I is going to be given by the expectation of I given n. And this is, again, this idea of just looking through the expectation operators to solve for the value that we want. And we can write out that double expectation as the expectation of the sum of the number of injuries per accident. Okay, given that we know that there are n accidents, then we can just sum over n to find that. So once we have that, then we can easily see that we take the expectation operator through that sum, and that means we just have n times the expected number of accidents the expected number of injuries in an accident. So we have n times the expected number of injuries in an accident, and so our final solution then is to take that and take the expectation of it, which means the expectation of n. So our answer then is simply the expected number of accidents per week times the expected number of injuries per accident will give us what we're looking for, which is the expected number of injuries per week. Okay? So we found the expected number of accidents per week times the expected number of injuries per accident. When we multiply the two, that gives us the expected number of injuries per week. And this is an example of how we use conditioning to find expectations.